The
Yeah,
sound and
so
everything.
let's start. So let me wait. So yeah, let's start the next talk. The speaker is Dominic Neuenfeld, and he is going to talk about the understanding the relation between semi-classical and quantum gravity through double holography. So please start.
All right. Well, thank you, and thanks to the organizers for hosting this meeting and inviting me to speak here. So yeah, as Tomoki already mentioned, I'm going to talk a bit about the relation between semi-classical and quantum gravity, mostly through the lens of double holography. Or in other words, what this talk's kind of trying to do is to take double holography, extract lessons from it, and then try to see how we can extrapolate this to, well, let's say, real life quantum gravity. So the things I'm going to talk about are mostly based on this paper down here, which appeared on the archive in May. And then that in turn is based on previous work, which appeared in April, and then also from last year with Vincent Chen, Rob Myers, Ignacio Reyes, and Josh Sander. Maybe as a starting point, and also a bit of motivation, let me start by pointing out that the question which sort of like really revolves around everything I'm talking about here is how to compute entanglement entropies for subregions in quantum field theories, in particular quantum field theories coupled to semi-classical gravity. So usually if we were just in scalar field theory, what we would do is we would ask questions like, what is the von Neumann entropy of a subregion A, which I've just like drawn here, so it's the spherical region. And if you want to compute this, what we do is we take the global state, rho, we trace over the complement of A, so the gray region, and that defines the reduced density matrix on A, which I call rho A. And from this, we can compute the von Neumann entropy of this region A, but we're computing minus trace rho A log rho A. And now this quantity, as you probably know, is ill-defined, has UV divergences, so we sort of like need to take care of those somehow. But morally speaking, we know what we're doing here, and we have like reasonably well control over what this von Neumann entropy is. And then in the last two and like really the last year, a novel method of computing entropies has emerged, which has its uses and has become sort of like the root of many new developments in semi-classical gravity. And this novel method goes by the name of the island formula. And so computing this, what I will call island entropy, is very different. It's oftentimes in literature, you see it called fine-grained entropy or quantum gravitational entropy. Here, I will just call it the island entropy because it's computed by the island formula. But so let me just quickly tell you how you use this and what you're actually computing. So the idea is you can define this new island entropy by doing the following thing. You fix some region A, again, here, but now instead of just computing the von Neumann entropy, you also consider all sorts of other regions, which I call I here. So this is an example of another region I could consider. Then you compute the von Neumann entropy of the quantum fields in A union I. But in order to include or in order to consider this island, you need to pay a penalty, which is given by the area of the boundary of this island over 4g Newton. What you then do is you extremize over all shapes and all sorts of islands I you can choose. And there's sort of one extreme you will always find, which is the situation where you choose your island to be empty, so there's no island, and then this formula reduces to the above von Neumann entropy. But then there are situations where you find non-trivial islands or non-trivial regions I here, which extremize this functional. And if you do this, then the formula instructs you out of all those different options you have. So you have an island, or you don't have an island, or you might have several different options of choosing islands. You choose the value for this functional, which is minimal. And this now gives you the island entropy. Okay, so why would we care? Why should we need a new formula to compute entropies? And the claim to fame of this formula is really that it solves the information paradox, in particular the black hole information paradox, in virtually all settings. Now, solves here is in quotation marks, because what I mean by solves is really it produces a unitary page curve. Now, let me quickly explain to you how this works. And I'll do this in some particular setting, which will also appear later in the talk, namely the setting of an eternal asymptotically anti-de Sitter black hole, which is coupled to a bath. So from a holographic point of view, what I can consider is a theory where I have some quantum field theory living on a line or maybe a higher dimensional space, which is rigid, and that's coupled to a conformal quantum field theory, which is holographic at its boundary. Now, if I have two copies of the system, I can entangle them in a particular way for them to form the thermophile doubled state. And the details are not important. What is important is that the holographically dual description of the system then becomes the following picture down here, where time runs upwards. And what you see here is in the green region, we have a gravitating region with an eternal black hole. So we have the left and the right part of the eternal black hole. And each of those sites is coupled to a bath region, here left in blue, right in pink, which can exchange quanta with the gravitational region, and which is at a fine-tuned temperature such that the black hole and this region here are in thermal equilibrium. So they exchange quanta all the time. They can fall into the black hole and also escape from the black hole. And now what I want to compute is the von Neumann entropy of the region A here, and this region A is defined to span the whole bath. And very roughly speaking, what I find if I follow this region A over time and compute its entropy at different times, I find that the entropy rises linearly, and that can qualitatively be understood fairly easily. The state on this background is entangled in a very particular way. So we have excitations here on the left and here on the right, which are entangled. So these two red excitations would be entangled the same for the two green excitations here. And most of them are either both in the region A or both outside the region A, and thus do not contribute to the entanglement entropy. But as time goes forward, let's take, for example, this red excitation here, it stays in the bath. So it stays in region A, it goes out to infinity, whereas the future time evolution of this excitation makes it fall into the black hole horizon. So up here it is, now it leaves the region A. And since one partner is in region A, one is outside, they contribute to the entanglement entropy. Now, the problem arises when we realize that the maximal entanglement entropy between the bath and the black hole is bounded above by the coarse-grained entropy of the black hole, essentially because the black hole can only purify so much of the radiation state. And that's given by 2 times S0, where I just called the entropy of the black hole S0. And so really, this red rising curve should never be able to go above this dashed line here, which upper bounds this curve. But of course, we see it happens, and so we have an information paradox where the entropy becomes bigger than it's supposed to be. Now, the add-in formula solves this problem essentially by, well, if you do the computation, you'll find an island which sits, which spans the complete interior of the black hole plus a bit outside the horizon. And so what's happening is that at late times, well before a particle just fell into the black hole and left the region A, now it falls into the island. And so the von Neumann entropy here essentially stays constant, right? So I take a particle out of A and put it into I, so nothing in here changes. However, the introduction of this island requires me to add this penalty here, which is the area of the boundary of I. Now, the boundary of I is just outside the black hole horizon. So this here really is essentially the black hole entropy. And what I find now is I have 2 sort of extrema of this functional. One, which I've discussed before, where I have no island. So that was on the previous slide. That corresponds to this rising curve here. And then the other one where I have this island, where I have some contribution coming from here, which is constant. And also here, I don't get a big contribution, but this stays very small and is also constant. And that is like the size of this is essentially 2 times the black hole entropy. And so this is my other extremum of this functional. And the Island formula tells me that the true entropy or the quantum gravitational entropy is given by the minimum of those 2 curves. And so we follow, follows this as the time evolution. So what we see is that initially the entropy rises, and then it saturates at a time which I will call the page time for this process. And this curve here also is the upper bound for how big the entropy can actually become. And so we've evaded our information paradox. Okay, so now that's all great, and one can like test this thing in a variety of different settings with different black holes and different theories of gravity, and so on and so forth, in different dimensions. But the problem is it doesn't really sort of like tell us why this is the right prescription. So there's essentially like, well, there's many questions which are still unanswered, and I want to focus on 2 of them. First of all, there's this question of, okay, so Hawking did a computation where just the outside entropy rises. So where did this go wrong? And a very modern answer you might hear to this question is, well, you know, he used the wrong formula. He should have used the Island formula, or equivalently, he should have done the computation using a Euclidean path integral with gravity, and then included replica wormholes. So I've drawn like a little sketch of this here. And then he would have got the right answer, and that's just equivalent to using the Island formula. But really, this is sort of just saying, well, if we use the Island formula, we get the right answer, but not why we should be using it. And so from the point of view of the Island formula, it's completely unclear, in particular because, well, we can do a computation and we can compute the entropy of, say, black hole radiation, of an evaporating black hole, and we just simply find that the state is mixed. And not only that, but the fact that the state is mixed is a very important ingredient in this part down here of the Island formula in order to get the right result. So the question still remains, what entropy is this Island really computing? Is this even an entropy? And why, if it is, why is this the right formula from a Hilbert space perspective? And then the second very related question asks how semi-classical gravity is even related to gravity, to quantum gravity in higher dimensions. Like what kind of approximation, if it is an approximation, what kind of approximation is it? And in 2 dimensions, we seem to be understanding this like fairly well. It's been shown by Schenker and Stanford that gravity in 2 dimensions, JT gravity in 2 dimensions is an ensemble average over different Hamiltonians, but it's really unclear how to sort of carry this over to higher dimensions. What would be the equivalent statement in 4 dimensions, in particular because within holography we have very explicit examples of single theories which are dual to a bulk theory. And then there are other questions about or other mentionings in the literature, interesting ideas that, you know, perhaps semi-classical gravity has something to do with observers which have which can only perform actions of low complexity or have some limited computational power, where they can only, for example, perform quantum circuits which are polynomial in the number of gates, but not exponential in the number of gates. Now, in order to tackle these questions, what I want to do here, and sort of like also propose more generally, is to use double holography to make progress. The double holography is essentially the single model in higher dimensions we have, where we kind of understand what the Island formula does, and because essentially the whole problem gets embedded into standard ADS CFT. Okay, so in terms of the outline, I'll start by reviewing double holography a bit. And then I will talk about how to compute entanglement entropies in double holography, and point out that there's a subtlety regarding the homology constraint one has to use for RT surfaces. And the subtlety has a bunch of interesting consequences for double holography, which I will discuss in the meantime. Then there's a qubit tunnel. Unfortunately, I won't have enough time to talk about this. So I mean, if somebody has questions after the talk, I'm happy to say a few words about this, but for now I will skip this part of the talk. And then at the end, what I want to do is I want to take the consequences we figured out for double holography and try to extrapolate them somehow to the relation between semi-classical gravity and quantum gravity to essentially make the point, well, if the real world works, at least very roughly, like double holography, this is what we should semi-classical and quantum gravity expect to look like. Okay, so let me start with a little introduction to double holography. Double holography is really sort of using two different ideas and putting them together. The first idea we're using is by Takeyanagi, and it's called the ADS-B-CFT correspondence. So there's a duality between a boundary conformal field theory, which possibly has some degrees of freedom at its boundary. So what you see here are time slices in the picture. And there's a dual description of the system in terms of an asymptotically ADS space with an end-of-the-world brane. The duality is in such a way that the asymptotic boundary here corresponds, at least conformally, to the geometry on which, like the ambient geometry of my boundary conformal field theory. And then where those defects here are at the boundary of the BCFT, we attach an end-of-the-world brane to the asymptotic boundary in the ADS perspective, and it sits at some particular location in the bulk. Again, the details are not horribly important, but can be found in the papers I cited in the beginning. How we model this essentially by saying this end-of-the-world brane has a constant tension term, and then we also, of course, need to add a Gibbons-Hawking-Yock term to make a variational principle in the bulk well defined. And the other crucial ingredient is that we choose Neumann boundary conditions at this end-of-the-world brane up here. But what this enables us to do is we can tune the tension and thereby changing the location of the brane such that if we increase the tension up to some critical value, this brane still gets closer and closer up here where the asymptotic boundary would have been, which now is excised by the end-of-the-world brane. Going to this regime essentially corresponds to increasing the number of degrees of freedom here located at the boundary, and also increasing the coupling of the theory, which I locate here at the boundary. Okay, so this is more or less standard ADS-CFT. But now if we go into this limit where this brane approaches the asymptotic boundary, something interesting happens in the bulk, namely that this D+1 dimensional gravitational theory here develops a new mode, a new graviton mode, which essentially localizes to the brane. And by that I just mean that the overlap of its wave function with a region very close to the brane becomes big and it becomes small everywhere else. Now, that has been realized by Cart and Randall based on earlier work by Randall and Sundrum. And so this gives rise to a new description of the system then in this limit, which looks as follows. We essentially have a CFT now living on the asymptotic boundary plus the brane, where the part which used to be the asymptotic boundary is just a fixed background, and the part where we're on the brane now couples to gravity due to this localization I've mentioned before. One way to convince yourself is you look at the on-shell metric, the on-shell action in the bulk perspective, and you just see that you can rewrite this as essentially a CFT partition function where the CFT is really only an effective CFT because it has a cutoff, plus some gravitational action, which at leading order looks like standard Einstein gravity in an ADS space, and then there are smaller subleading curvature corrections, which can also be computed. Okay, and so during this talk, I will sort of like use these three descriptions, and I will give them names, which are up here. So I will call this the boundary perspective because we have a boundary CFT. I will call this the brane perspective because we try to pretend that we're living on the brane. And I'd really be interested in sort of like the induced duality between those two pictures. And in order to find this induced duality, I will oftentimes refer to the bulk picture here, which I call the bulk perspective. Secondly, I want to talk about the island formula. So I need a setting where the island formula gives me non-trivial results. And the easiest way of doing this here is by introducing a black hole in my bulk space-time. And in this particular model, the absolutely like 0th order easiest thing you can do is you just go to the bulk perspective and look at the bulk perspective in ADS Rendler coordinates. So we find a horizon here, and I've just drawn the bifurcated horizon as this red dashed line. Now, what this means in the boundary perspective is that I essentially split my system into two parts, to the left and to the right, which are entangled and which are entangled in the thermophile double state. Now, what this means for the brane perspective is that I have my gravitational region on which I have an internal massless topological black hole, which is just induced from the bulk metric onto the brane, then coupled to these two rigid regions where I don't have dynamical gravity, which are also entangled. But yeah, there's no dynamical gravity. I will call them the bath region, and they're in thermal equilibrium with a black hole induced on this brane. Now, this might be a bit hard to see from these pictures, but still, let me just give you a three-dimensional perspective, at least as far as my artistic skills allow me to. So in the boundary perspective, we have the left BCFT here in blue, the right CFT here in pink, and then the degrees of freedom at the boundary here and here. So time in this picture runs upwards. Then if I go to the bulk perspective, what happens, I get this sort of like typical cylinder I get from global ADS, but where now those boundary degrees of freedom here, so I've get replaced by this green brane, which runs through the bulk and is very, very close to the asymptotic boundary in the back. And from the brane perspective, or I get the brane perspective by just taking the union of the asymptotic boundary and the brane and sort of unwrapping this from the cylinder. And what I find is then in the green region, which is my brane used to be in the bulk perspective, I get this eternal black hole. I've drawn the horizons here as black lines. And then the left part of the eternal black hole is coupled to the left bath. The right one is coupled to the right bath, and they're in thermal equilibrium and can exchange quanta. Okay, that might be a good place to briefly stop if there are questions about the setup. And if there are none, then let's go on and try to understand how one usually derives the island formula in this setting. And what one does is one goes to what I call the boundary perspective, selects some region A and asks, okay, what is the von Neumann entropy of this region? And the answer to this is given by Takiyanagi. And the answer is that you can just use the standard RT formula, you know, from ADS-CFT to compute the von Neumann entropy. And what this instructs us to do is to find a surface in the interior, codimension 2, which extremizes the area functional. And if we find many, we take the minimal surface, evaluate its area, divided by 4 Newton, and this gives us the entropy. Now, there's a little twist in the case of ADS-BCFT, namely that usually in ADS-CFT, this codimension 2 surface needs to be homologous to the region A, meaning that A and the surface need to enclose some partial Cauchy slice, which I called sigma A here. But in the case of ADS-BCFT, this homology constraint only needs to hold up to regions in the brane. So here you see that chi A and A, they do not quite completely enclose a partial Cauchy slice here, but that's okay because the missing part of the boundary lies within the brane. Okay, and so one can now use this to compute the von Neumann entropy as a function of time. So we fix the region A in Riddler coordinates. And what we see is the following. We see that initially this here, so there's the RT surface which caps off region A is the dominant one. It grows linearly with time. This is a standard calculation due to Hartmann and Maldacena. And then after some time, there's going to be a phase transition where now the smaller surface is given by the one which connects to the brane. So it consists of these two pieces here. This is the length of this is constant in time. And so we see this behavior we saw before using the Allen formula where the entropy grows and then at some point, which we call the page time, is constant. Now, so far, I haven't talked about black holes, just told you that for this quantum mechanical system, we can derive the von Neumann entropy. So now how do we bring black holes into the picture? We interpret our findings within the brane perspective. So we go to this brane perspective and try to understand, well, what does this RT surface here, which I will call the island RT surface, mean? Well, the area term consists essentially of 3 pieces. One piece is very close up here to the boundary, It's large but finite. And it turns out that from the point of view of brane coordinates here, this can be rewritten as the area of the boundary of this region I, which I define to be the intersection of the shaded red region with the brane, over 4G Newton on the brane. So this is an area term, and then there's higher curvature corrections, which exactly map sort of like the leading contributions to the generalized entropy you would expect in a theory of gravity with corrections. Then there's another contribution down here, which comes from very close to the brane, which is divergent, in fact, and these are just UV divergences coming from the quantum field theory, which lives in the Bath region here. And then there's sort of like the bulk part of this RT surface, which can be interpreted as giving us the entropy between quantum fields on a union, this small region I. So this sort of shows that the result is the same as the result of the island formula, except for like a small subtlety, but which you can also prove. Namely, you can show that that extremizing over the shape of the island in this perspective really is the same as extremizing over the location of the RT surface here back at the brane, or essentially is the same as the extremization procedure you would have to use from the bulk point of view. But now or maybe that's again a good place to just, in case some questions come up. Okay. So, but now let's get to the sort of like main part of the talk, namely trying to understand what we've actually done. So what we've done is that we computed the von Neumann entropy of some subregion A, where the subregion was defined in the boundary perspective. And then we've taken this result and reinterpreted it in the brane perspective. So what we learn from this is that this island RT surface computes the von Neumann entropy of a region A in the boundary perspective after the page time, but it does not, at least not necessarily or not obviously, compute the von Neumann entropy of a region A in the brane perspective. And moreover, it's not even clear that it computes any sort of entropy in the brane perspective. And in fact, one thing I want to convince you of first is that choosing this particular RT surface here, so this island RT surface, shouldn't be a valid choice if we want to use RT to compute entanglement entropies of regions A in the brane perspective. And in order to show this, I need two, I think, very mild assumptions. The first assumption is that this brane perspective should be described by some semi-classical quantum mechanical theory, and that there's a unitary map between what's called the code subspace, which is called the space of quantum fluctuations in the bulk, to the Hilbert space on the brane. Now, the reason I need this is essentially that I want to avoid cloning. So we used to this from standard ADS CFT, that information in the boundaries, encoded in the bulk in sort of a particular way, and it's not cloned. And I want to maintain the same thing when going from the bulk to the brane perspective. And then secondly, I want to use some standard rules of what's called entanglement wedge reconstruction. So what entanglement wedge reconstruction just tells you is that the bulk quantum state in the entanglement wedge, which is this red shaded region here, so it's the region enclosed by A and the corresponding RT surface. The information about the quantum states in this entanglement wedge can be reconstructed in the boundary from region A. So, and there's two sort of like corollaries from how this works. One is what's called entanglement wedge complementarity. What this tells you is that everything I can reconstruct, or everything in here, which I can reconstruct from A, I shouldn't be able to reconstruct from the complement of A. And the second is entanglement wedge nesting, which just tells me that if I can reconstruct, or if I cannot reconstruct something from the region A, I also shouldn't be able to reconstruct it from a smaller region, which is contained within A. So subsystems in the boundary essentially correspond to subsystems in the bulk. Now the claim is that if we take the brane perspective, this island RT surface, or that this here is the correct RT surface, is an inconsistent choice. And the argument is very, very simple. Namely, we just observe that if I have some operator, say in the bulk, I want to reconstruct in terms of the boundary, then if this operator is in the entanglement wedge of A up here, I should be able to do this in A, which means also that I should not be able, and this is now by entanglement wedge complementarity, I shouldn't be able to do this in the entanglement wedge of A bar, or in other words, the information shouldn't be contained in A bar. Now, in order to understand what A bar is, let's look at this picture on the right here, the brane perspective. It's everything but A. So it's this part of the bath, and then it's part of this gravitational region up here, and then a bit more of the bath. And so in particular, if I cannot reconstruct phi from the complement of A, I shouldn't be able to reconstruct it from this region B up here. However, it turns out, and again, I'm not going into the details very much, is that by knowing information in this region B, such as one-point functions of operators and such as values of the metric and other sources, I can actually integrate the equations of motion into the bulk of it and reconstruct the operator phi just in terms of data in this region B by a procedure called HKLL, which is a particular way of bulk reconstruction. So what we've shown is that although I shouldn't be able to reconstruct any information about phi from the complement of A, I in fact still can do it. So there's a contradiction. And now we want to resolve this contradiction. And well, one option is, of course, to do away with one of the assumptions I've made, but I do want to keep them, in particular the second one about entanglement wedge reconstruction, because this really is at the heart of this island formula. But there's another option I can do, which is I just forbid this particular type of RT surfaces. And I can do this by modifying the homology constraint. What I mean by this is I'm saying I can compute the von Neumann entropy of a subregion A in the bulk, just by the usual RT formula. But if I want to compute the von Neumann entropy of a subregion A in the boundary perspective, so where I just have the BCFT living down here, then my RT surface has the weaker homology constraint in that it can end on the brane. So it only needs to be homologous to A up to terms in the brane. Whereas if I want to do this in the brane perspective, I do not allow this weaker homology constraint. Instead, what I want to do is I want to essentially do standard ADS-CFT by treating the brane as well as the asymptotic boundary as a boundary. What this means in practical terms is that in the boundary perspective, if I want to compute the the entropy of a region A, I have two possible candidate RT surfaces, one which just caps off A, and the other one which connects to the brane. Whereas if I want to do the same thing for the same region, but in the brane perspective, I only have one single choice, and the von Neumann entropy is just given by this particular surface here. Okay, so this has some consequences for all sorts of different things. So let me go through a few of them. The first thing is maybe discussing how we can reconstruct operators. And in order to do this, it's useful to split operators into two different classes. One class we will call simple operators, the other class we will call complex operators. Now, the simple operators are those defined in what is called the outer wedge, and that's simply the region between A and this extremal surface, which is the outer extremal surface, so the one which is closest to A. So every operator which has a representation within this region, I will call a simple operator. And one can essentially show that by using simple bulk reconstruction techniques, the reconstruction of these operators as operators on the boundary here should be the same in the boundary or in the brane perspective. And there's a second class of operators, which I will call complex operators, and these are the ones which live in what's called the Python slunge. Now, this is this name is due to the Python slunge conjecture by Brown, Gabarian, Pennington, and Susskind. And what they said is that if we have an entanglement wedge, well, we have a non-minimal extremal surface somewhere. So that's the case here, right? This is our entanglement wedge. It's this big region here, but then there's another extremal surface which lives somewhere in my entanglement wedge. Then everything beyond this outermost extremal surface is exponentially hard to reconstruct. So if I want to do it with a quantum circuit, my quantum circuit needs to be, we need to have an exponential number of gates. And so therefore, I'll call these operators complex operators because in, let's say, practical terms, any observer who lives on the boundary will have a very, very hard time to reconstruct this operator. Might even be impossible. Okay, but what we see now here is that where in the boundary perspective, information about this operator or the operator itself can be reconstructed from this region A. This is not possible anymore in the brane perspective because my entanglement wedge doesn't reach all the way up here anymore. Instead, there's this different region, this region B I've introduced earlier, which I can use to reconstruct this operator. So what I see here is that complex operators map non-locally, right? So like initially it was encoded in region A. In the brane perspective, it's now encoded in some region B. And there's another important lesson we learn, namely that the island, so this intersection up here of the entanglement wedge with the brane, is not accessible from the bath in the brane perspective. While in the boundary perspective, it is accessible from the path. Now, why is this? And the answer is very simple, because the quantum state and the region A differs between those two perspectives, right? They're dual to each other in the quantum state, so it gets non-trivially translated. In the boundary perspective, after the page time, so this part here, right? The quantum state in the region A also encodes part of the lunge up here, whereas in the brane perspective, it only really encodes a simple state. In a sense, I will make clear soon. And then, so we can ask, well, what happens with this part of the lunge up here? And that in the brane, from the brane perspective point of view, just gets encoded in this gravitating region up here. So what we see is there's a different encoding of the same bulk state into different boundary degrees of freedom, whether we go to the boundary or the brane perspective. As a consequence of this, the von Neumann entropies are different in both cases. So the one in the boundary perspective we've already discussed, right? This is how we derived the island formula initially before the page time. This is the dominant RT surface. It grows linearly. So that's what we see here. And then at some point, there's a phase transition to this island RT surface, which is constant in time. And so the growth saturates. But on the brane perspective, this is not a valid configuration. So if I want to compute von Neumann entropies, I'll just see that the thing grows linearly without bound. Okay, now the other thing I mentioned before is that there's a duality between the boundary and the brane perspective. And so you might be asking, okay, so maybe the von Neumann entropy isn't the same, but is there maybe a way of computing the von Neumann entropy in the boundary perspective, but just from data given to me in the brane perspective? And the answer is yes, and we've in fact seen this, how to do this, namely, if we go to the boundary perspective, we've seen that the von Neumann entropy in the boundary perspective is the entropy, or is the same as the number we get if we compute the island entropy in the brane perspective. And so what the upshot of all of this is that the von Neumann entropy in the boundary perspective is dual to the island entropy in the brane perspective. Now, I want to make this sort of like statement particularly clear, because I think it sounds trivial, but it's not quite trivial, right? The statement here I'm making is that the island entropy doesn't really have any intrinsic meaning in the brane perspective. It's just a thing I can compute when I follow this rule here, but it doesn't mean much. It gets a meaning if I realize, oh, there's a different duality frame, which I call the boundary perspective here, where this agrees with my von Neumann entropy. And then we can ask a very similar question, just the other way around, namely, is there a way of computing the von Neumann entropy in the brane perspective, but now just given data in the boundary perspective? And again, the answer is yes. In order to understand how we can do this, the only thing we need to realize is that in the brane perspective, the entanglement entropy was given by this extremal surface, which also happened to be the RT surface. Now, in the boundary perspective, after the page time, well, before the page time, we get the same result. So there we don't need to worry. But after the page time, the RT surface is different. However, this other extremal surface still exists. The point is only, it's not the minimal extremal surface. It's a non-minimal extremal surface. But if we compute its area, we'll get the same results in the brane perspective. And now what we need to understand is what is the interpretation of this non-minimal extremal surface in the boundary perspective. And luckily, other people have asked these questions a couple of years ago in 2017, and namely Netta Engelhardt and Aaron Wall. And then there's been follow-up work this year by Engelhardt, Pennington, and Shabazi Moghadam. And what they argue is that the area of this surface computes what is called the simple entropy. And I won't tell you exactly what it is, but for the purpose of this talk, it suffices to know that this is a sort of coarse-grained entropy. So what is happening here is I want to find a quantum state with maximal entropy under certain constraints, and the constraints are such that this quantum state needs to correctly reproduce certain one-point functions in the presence of certain sources. And so again, we find a duality now between the von Neumann entropy in the brane perspective and the simple entropy, so a coarse-grained entropy in the boundary perspective. Okay, so let me, I have like 10 minutes left, that's perfectly fine. Let me give you some intermediate summary just about double holography and sort of like the state of what we've seen. So what we've seen is that there's a duality between the brane and the boundary perspective. And we can have simple observables or ask simple questions, if you will. And for those questions, if you ask them in the bath, this duality is trivial. Simple operators map to simple operators, coarse-grained states map to coarse-grained states. That's all fine. But now it becomes non-trivial if I ask for certain complex observables in the bath. And in those cases, depending on which direction you go, this duality involves one of three things. Either non-locality, so this is when I want to compute something, well, if I want to compute a quantity in the boundary perspective from the brane perspective, one example would be the von Neumann entropy, right? The von Neumann entropy in the boundary perspective can be computed in the brane perspective as the island entropy. But the crucial observation is that in the boundary case, to compute this thing, I only need the quantum state on the region A and nothing else. Whereas in the brane perspective, using the island formula, I don't need much more. I need to know the global state. I need to know the geometry away from the region A. So there's some like non-local duality going on. And similarly, if I have some complex operator in the region A, then in order to compute the same operator, but now from the brane perspective, I need access to this island or the gravitating region, which I've drawn in green on the previous slides. If I want to go the other way around, if I want to compute something, a quantity in the brane perspective from the point of view of the boundary perspective, then it involves some coarse graining. And we've seen this. If I want to compute the von Neumann entropy in the brane, then the dual question, the boundary perspective, is computing the simple entropy, which is a coarse-grained entropy. Now, the important upshot here is that the information about this island, so the information about the lunch and so on, is accessible from the boundary perspective after the page time in the bath. So if I have access to the region A, after the page time, I can reconstruct stuff in the island region, in the Python's lunch. But it's not accessible, and in fact, it's never accessible in the brane perspective. Okay, so let me just pause here, take a sip. And then go to the last part of my talk, which is now taking this picture and trying to extrapolate this to semi-classical quantum gravity. The first question, of course, is how would we even do this? What seems like a reasonable extrapolation? And that would be that we identify or we associate the brane perspective to semi-classical gravity. Now, why would we do this? Because in both cases, we're using the island formula to compute a unitary page curve. And then something which I pointed out, but maybe didn't like really emphasize a lot, was that if we do the semi-classical computation of the entropy of Hawking radiation, say, or radiation which comes, which is in the bath in our case, it grows without bound. And the same we've seen from the brane perspective. There, the entropy also grew without bound. So qualitatively, those two pictures behave very similarly. So let's say, everything that's true for the brane perspective should roughly also be true for semi-classical gravity. And then similarly, we can make arguments to associate the boundary perspective to quantum gravity. In both cases, we would really like to be able to compute the page curve, not from some obscure like island formula, but from a simple von Neumann entropy. And in particular, well, we've seen that this is possible boundary perspective, and in quantum gravity would just like to collect Hawking radiation, feed them into a quantum computer, say, and verify that this is a pure state. Then the second thing is that the brane perspective is related to the boundary perspective by some sort of coarse graining, at least for regions in the bath. And that fits very well with our intuition about the relation between semi-classical gravity and quantum gravity. And lastly, this boundary perspective from the point of view of ADS-CFT really served as a microscopic description of the system, and we expect the same thing to be true for quantum gravity. Whoops. Okay. And so, yeah, let's just like take this identification and let's go through what this would mean. What we find is that we have two dual descriptions now, quantum gravity and semi-classical gravity. So it's not like semi-classical gravity is like strictly an approximation to quantum gravity, but there's some sort of duality going on. And they're related non-locally, just in the same way the boundary and a brane perspective were related non-locally, by taking information and storing them or rearranging them into different degrees of freedom, which are also located in different parts of the spacetime. Now, from the point of view of semi-classical gravity, the outside of the black hole, at least after page time, just looks like a coarse-grained state. But in fact, this information we have there is not lost. It's just been used, so the complex information this region would contain in the quantum gravity has just been used to reconstruct the black hole's interior or the island. And then, again, as we've seen in the previous example, one should expect then that complex operations in quantum gravity can translate non-locally in semi-classical gravity, and we've seen the examples of von Neumann entropy and also complex operations. And so the upshot of this would just be quantum gravity. That would be some sort of like fundamental stringy, perhaps, prescription. It's very good for all sorts of questions you want to ask outside the black hole. But the point is, you don't really have a black hole interior. And sort of by analogy to the doubly holographic setup is, right, if you want to identify quantum gravity with a BCFT, with a boundary perspective, then we see that there we didn't even have a gravitating spacetime. Instead, the gravitating spacetime just got replaced by these quantum mechanical degrees of freedom at the boundary. And so if you want to extrapolate this and, like conjecturing a bit, then, perhaps this shows that really in quantum gravity, we have some stretched horizon or maybe some fuzzball or whatever, which replaces a black hole. But then there's also the semi-classical description. And now outside of the black hole, this really is an approximation which is only good for simple observables. So as if I have an observer which is computationally bounded, that's fine. But if they can do exponentially complex, if they can ask exponentially complex questions, it's not a good approximation anymore. But I can still have access to a very complex question I can ask, except that now I need to go inside my black hole and ask the questions there. And most crucially, in the semi-classical picture, information never leaves the black hole in the sense that just by having access to the radiation, I cannot access the black hole interior. I cannot, read off what's going on in there. So to end my talk, let me...
Sorry.
Yeah.
But you're finishing, but anyway, you left this to me. Just I forgot to inform you.
Oh yeah, that's fine. This is my last slide. Okay, so right, so just to sort of like end the talk, let me start with the two questions I started out with and just answer them in opposite order. So from this perspective, if you want to ask what is semi-classical gravity in higher dimensions, then the answer is something like it's a reorganization of states in quantum gravity into some new set of degrees of freedom in such a way that simple, low energy observables or operations are correctly reproduced in semi-classical gravity outside the black hole. In order to reproduce complex questions, we need to have access to the interior of the black hole. And then secondly, the question where Hawking's computation went wrong. has an answer which is simply, well, nowhere. It's like a completely fine computation. The point is just that it has been done in the semi-classical description, which is not apt for answering questions about, purity of states and so on, because these questions are very complex questions. In order to answer them, we really should be using some formulation of quantum gravity, which, well, we don't really have yet. Okay, so that's all I want to say. Thanks for listening. Yeah.
Thank you. Already nice talk. So, is there any questions or comments from the audience? If there are no question or comments, so let's thank the speaker again. Thank you. Dominique.
All right. Thanks a lot.